Hello everyone. Today I'm going to talk about row reduction and echelon forms. These are part of a famous algorithm called Gaussian elimination, which will be used to solve linear systems. Um, Sometimes real-world problems, they can be transformed and modeled into a linear system. But the thing is that these linear systems, they are usually huge with lots of variables and unknowns. And if you want to solve them on the computer directly, it might take an awful amount of time, and the computational complexity is like large. So instead of doing that, you can use Gaussian elimination algorithm to start, like when you start with a linear system, you use this algorithm to get an equivalent system to the first one, but this system that you end up with, it is much easier to deal with. It is like you're not changing the solution set, it's just somehow simpler. All right, in order to do that, we are allowed to use three operations and only these three operations that we know. These are elementary operations, we learned about them. So I'm just gonna write them down. The first one, as you know, is interchanging. The next one is replacement. And the third one is scaling. Okay. But instead of using or applying these elementary operations directly on the linear system, we are going to apply it on a special matrix corresponding to this system. Okay, so let's see how this works on this example. But let's see what is that matrix. So this matrix, this special matrix, has two parts. The first part is the coefficient part. So you can put the coefficients of equations into one single matrix. So let's see what is that matrix. In this matrix, each row corresponds to an equation. So row 1 corresponds to equation 1, row 2 corresponds to equation 2, and row 3 corresponds to equation 3. And the columns are corresponding to the variables. So first column corresponds to x1, second column corresponds to x2, and third column corresponds to x3. All right, okay, let's write down the first row. Look at the first equation, okay? The coefficient of x1 in first equation is 3, so I put 3 here. The equation of x2 in equation 1 is 6, I put 6 here. And the equation of x3 in the first equation is 9. So this forms the first row. You repeat the step for the other equation. So put the coefficient 2 here, 4 here, 5 here, and then look at the last equation, the coefficient of x1, the coefficient of x2, and then the coefficient of x3. Okay, so this matrix is called the coefficient matrix corresponding to this system. Now, for the second part, I can put all the constant in one single column. So the constant of the first equation, the constant of the second equation, and the constant of the last equation. They all form this column, which is called constant column. Okay, now if we take these two and glue them together, we form a bigger matrix called augmented matrix, and that's the one we're going to work on. So I'm going to glue them together. And this whole matrix is the augmented matrix. So the whole thing here called augmented matrix corresponding to this linear system. All right, now I can apply this elementary operation on this matrix. Okay, so when I say interchanging, okay, I mean that we can interchange two equations, right? So here in the matrix, each row correspond to an equation, meaning that I'm allowed to swap two rows here, right? And by replacement in the system, we know that it means that we can add a multiple of one row to another row, right? So in the matrix, I'm allowed to add a multiple of one row to another row, okay? So the third one is scaling, which means that I can multiply one row by a non-zero real number, right? The same thing for this linear equations. All right. The goal is to end up with this reduced system, right? So look at this system. Here, the coefficient of x1 is 0, right? I can write x0, x1 plus the rest. And for the third equation, I have 0, x1 plus 0, x2, and then plus the rest, okay? And if you look at that, it looks like a staircase form. So in this staircase form, everything under the stairs, or the coefficients of the variables on the stairs, they're all 0, okay? So the matrix we want to end up with should look like something like this. Everything under the stairs, there are 0. I have one here, and one here. And these can be like anything. I don't care about these ones. So this is the form we are looking for. All right, so let's start applying these operations, elementary operations. All right. Usually we start with the upper left and end up with the lower right, similar to what we have here, right? Upper left to the lower right. The first step you need to do is to look at the first non-zero entries of each row, okay? So the first non-zero entry of the first row is this one, the second one is 2, and the third one is 2 again. And we want to pick the row in which the first non-zero entry is closest to the left, okay? In this case, they are like all at the same position. So I'm going to just stick with the first row, okay? And I'm going to pick the first non-zero entry of that row, which is called the leading entry of that row. And I'm going to use this to make these two to be 0, right? I want to end up with something like this, right? The first column to be like 1, 0, 0. So to make it easier, I'm going to make this as 1, or in other words, I'm going to scale this one. So I'm going to use scaling. So row 1 is scaled by 1 over 3. So the new matrix looks like 1, 2, 3, and 5. And I just rewrite down the other rows. Okay, I'm going to use the leading entry to make these two to be 0. And in order to do that, I am going to use replacement. So for the second row, right now, let's focus on the second row. I want to make this 0 using the first row, the row that the leading term is in it, right? So if I add -2 of row 1 to row 2, I can make this 0. So the the operation we are using here is R2 being replaced with R2 plus -2 times R1. Okay, so it looks like this. I'm not changing the first row, I'm just going to rewrite it. Now, let's apply this operation. 2 minus 2 times 1, 0. 4 minus 2 times 2, so 4 minus 4, 0. 5 minus 2 times 3, which is going to be 5 minus 6, is going to be -1. And the last one 11 minus 5 times 2. So it's going to be just 1. All right. Now, move to the next row and use the replacement to make this 0. So to make this 0, I'm considering row 1 and row 3. So I need to add a multiple of row 1 to row 3 to make this 0. Okay? And similar to the previous case, it's going to be the operation R3 being replaced with R3 plus negative 2 times R1. So 2 minus 2 times 1, 0. 6 minus 2 times 2. 2 minus 3 times 2. So 2 minus 6 is going to be minus 4. And the last one, 4 minus 2 times 5. So 4 minus 10 is going to be minus 6. All right, so look at this. I have this leading entry, everything under it is 0. So we are done with the first leading entry or the first row. Okay, now we need to repeat this step for the other rows. Okay, again, so for here I look at the rest, right? I look at the other rows, the remaining rows, and pick the one in which the leading entry or the first non-zero entry is closest to the left. So here, this is the leading term for row 2. This is the leading entry for row 2. I'm going to bring this up. I'm going to swap the place of these two rows. So I'm going to replace row 2 with row 3. So I'm not changing row 1. And then 0, 2, minus 4, minus 6, and then 0, 0, negative 1, 1. All right. Now, this is 2. I'm going to normalize it to make it as 1. So I'm going to use scaling. So row 2 is being scaled by 1 over 2. So the new matrix looks like this: 1, 2, 3, 5. Divide everything by 2. So I get 0, 1, negative 2, and negative 3. And I just rewrite the third row. Okay, we are almost done. So look at this leading entry now here. It is 1, and everything under it is 0. Okay, so we are done with this leading entry. Okay, move to the next row. The leading entry is going to be negative 1. I'm going to just normalize it. So I have row 3 being scaled by negative 1. So I get 1, 2, 3, 5. 0, 1, negative 2, negative 3. 0, 0, 1, negative 1. All right, now look at this matrix. This is exactly the form we wanted, right? So in each row, we pick the leading entries, made everything under it to be 0. There is nothing under this one, so we just leave it as it is. And this form is called echelon form. So the goal was to end up with the echelon form or the staircase form, right? Now, I can write down a system based on this matrix and then solve the solution using back substitution. Okay, so here, let me erase this part. I know that the first row corresponds to equation 1, the second one to equation 2, the last one to equation 3, and column 1 corresponds to x1, column 2 x2, and column 3 x3. Okay, so from the first row, I get, so these are the coefficients of x1, x2, x3 in equation 1. So I get 1 times x1 plus 2 times x2 plus 3 times x3. And then I have my constant term. So this is equal to 5. This is the first equation. The next row corresponds to the second equation. So I have 0x1. I just don't write it down. Then I have 1x2. Then minus 2 times x3. And this is equal to the constant term minus 3. Okay. And the last row, I get 1x3 equal to negative 1. So x3 equal to negative 1. Okay. Compare this with this system. This is exactly the system we wanted, right? The reduced version. Now, we are going to use back substitution. So I'm going to just write it down here. Using back substitution, we're going to solve the system. So I start with the third equation. So from the third equation, I can get x3 to be negative 1, right? Now, I get the result of this equation and plug it in the previous equation, second to the last equation. So this is equation 2. So from equation 2, I have x2 minus 2 times x3 equal to negative 3. And I know what is x3 from equation 3, right? So I can replace this with negative 1. So I get x2 minus 2 times negative 1 equal to negative 3, meaning that x2 is minus 3, which is minus 6, right? Now, I used the result here. I plugged in equation 2, got x2. Now I have x3, x2. Use them and plug them in equation 1 to get x1. So from equation 1, I get x1 plus 2 times x2 plus 3 times x3 equal to 5. So I have x2 and x3 from the previous steps. So I just replace them. I get x1 plus 2 times x2 plus 3 times x3 equal to 5. I just need to solve this. So I get x1 minus 12 minus 3 equal to 5. So x1 equal to 20. Okay. Now I got the solutions for all variables. I put them all together in one single column. So x1, x2, x3. This is equal to x1 is 20, x2 is minus 6, and x3 is negative 1. And that's our unique solution of the system. Okay. Yeah, before I just forget, I just want to mention that this is the echelon form of the augmented matrix, or row echelon form. And you usually show this by R, row, E stand for echelon, and then F stand for form. So this is called REF. All right, now that we have seen an example how to get the REF, the row echelon form, let's see the official definition. Let's see the definition. Row echelon form, or REF. A matrix of size m by n So I mean that the matrix can have any size. It can be a rectangular matrix. So a matrix of this size is in row echelon form if we have these three conditions. First, all 0 rows are at the bottom of the matrix. So if somewhere in the middle of the process you get a 0 row, you have to use the interchanging to put it on at the bottom. Second, in a column, all entries below a leading entry must be 0. So if you have a column which includes a leading entry in that column, everything under the leading entry must be 0. Okay, so I'm just going to add if there is a leading entry in that column. Okay, and the third condition is that a leading entry, or let me say, any leading entry must be to the right of all leading entries in the rows above that row. That includes the entry. So if we have these three conditions, then we say that the matrix is in row echelon form.